Every star you've ever looked at follows one basic rule: the brighter it burns, the hotter it is. Except that's wrong. Red giants are some of the most luminous objects in the entire galaxy, and they're cooler than the sun. Today I'm breaking down every phase of red giant evolution, from the first expansion to the final collapse, starting with the phase that breaks everything you thought you knew. Red giant branch stars. Here's the thing about stars. They spend billions of years on the main sequence, fusing hydrogen in their cores, behaving themselves, following the rules, and then they run out of fuel and completely lose their minds. A star between 0.4 and 12 solar masses enters the red giant branch after it exhausts the hydrogen in its core. What's left is an inert ball of helium just sitting there, doing nothing, while a thin shell of hydrogen around it picks up the slack and starts fusing like its life depends on it, which technically it does. Once the RGB phase kicks in, things get genuinely strange. At the base of the branch, surface temperatures sit around 5,000 Kelvin. By the tip, that drops to approximately 3,000 Kelvin. Meanwhile, luminosity skyrockets to 2,000 to 2,500 times the sun's output, brighter and cooler simultaneously. Plot this on a Hertzsprung-Russell diagram, and the star traces a nearly vertical line straight upward. It completely contradicts the intuition that brighter should mean hotter. The reason is radius. The core contracts, the envelope expands, and the star balloons to absurd proportions. Same energy output gets spread across a vastly larger surface area, so each square meter is cooler, but there are so many more square meters that total brightness goes through the roof. It's like replacing a blowtorch with a warehouse-sized space heater. And the star doesn't just sit there getting bigger, it's actively falling apart. Total mass loss during the RGB phase reaches 0.2 to 0.25 solar masses, most of it crammed into the final million years before helium ignition. On top of that, something called the first dredge-up occurs, where convection drags processed nuclear material from near the core up to the surface. This visibly changes the star's chemistry, altering the carbon to nitrogen ratio in a way you can literally measure with a spectrograph. The star is rewriting its own surface composition in real time. So to recap, it's bigger, cooler, brighter, losing mass, and chemically rearranging itself all at once, which is, not ideal for stability. But at least red giant branch stars eventually reach helium ignition and settle down. The horizontal branch, on the other hand, is where things get truly weird. Asymptotic. Giant branch stars. This is where stars go to fall apart. The asymptotic giant branch is the final major evolutionary phase for stars between roughly 0.8 and 8 solar masses, and it is, without exaggeration, the most unstable thing a star can do before it dies. Everything about this phase screams ticking time bomb, and the fuse is already lit the moment a star gets here. Here's what makes AGB stars so fundamentally different from everything that came before. The core structure is layered like the worst onion you've ever peeled. At the center, you've got an inert carbon-oxygen core just sitting there doing absolutely nothing. Wrapped around that is a helium-burning shell. Above that, an inert helium layer. And then on the outside, a hydrogen-burning shell. Two nuclear furnaces separated by dead weight, both trying to power the same star. The problem is they can't both run at the same time. Every 10,000 to 100,000 years, the helium shell becomes unstable and ignites violently in what's called a thermal pulse. The star's energy production flips between hydrogen fusion and helium fusion in a repeating cycle that never stabilizes. It's a star at war with itself, two engines fighting over the same machine, and every time one kicks in, the other shuts down. No earlier evolutionary stage does this, not the main sequence, not the red giant branch, not the horizontal branch. This is new, and it's inherently unsustainable. And the size of these things is genuinely absurd. GB stars can expand to radii approaching 1 astronomical unit. That's the distance from the sun to the Earth. If our sun were on the asymptotic giant branch right now, its surface would be where you're standing. You wouldn't be orbiting a star. You'd be inside one, which is, not ideal, but here's where it gets even wilder. Each thermal pulse dredges material from deep inside the star up to the surface. After enough pulses, so much carbon gets dragged upward that it actually reverses the carbon to oxygen ratio in the outer layers. The star literally changes what it's made of. These are carbon stars, and they're walking proof that AGB stars don't just burn differently, they transform chemically in real time. Meanwhile, the star is hemorrhaging mass at a rate that's almost hard to believe. Pulsation-driven winds and radiation pressure on newly formed dust grains strip away 50 to 70% of the star's total mass. Long-period variables on the AGB pulse over hundreds of days, their brightness swinging wildly as luminosities hit several thousand times solar. The star is bloating, pulsing, shedding its own body, and rearranging its chemistry all at once. It's not evolving anymore. It's disintegrating in slow motion. But if you think a star tearing itself apart over thousands of years sounds dramatic, wait until you see what happens when stars 8 times heavier than the sun hit their final chapter. Aldebaran is only 16% more massive than the sun. That's it. 16%. And yet it's 439 times brighter. If that doesn't immediately tell you that mass isn't the whole story when it comes to stars, nothing will. See, Aldebaran is basically a preview of what our sun is going to look like in about 5 billion years. It started out as a fairly ordinary star, just slightly heavier than ours, burned through its core hydrogen, and then did what all stars in that weight class eventually do. It swelled a lot. Its radius ballooned to 45.1 times the sun's diameter, roughly 63 million kilometers. That's about 40% of the distance between Earth and the sun. This thing would swallow Mercury whole and keep going. But here's what makes Aldebaran genuinely useful for understanding red giants. It's close. Only 65.3 light years away, which in astronomical terms is basically next door. That proximity means we can study it in absurd detail, and it actually serves as the official spectral standard for K5 giant stars. Every other star in that class gets compared to Aldebaran. It's the measuring stick. Its surface temperature sits at 3,900 Kelvin, noticeably cooler than the sun's 5,778 Kelvin, which gives it that deep orange-red color you can spot with the naked eye in Taurus. It rotates at a pace that can only be described as glacial. One full rotation takes 520 days. The sun does it in 25. Now, when astronomers look at Aldebaran's chemical makeup, they find exactly what they'd expect from a star that's completed its first dredge-up. Nitrogen levels are elevated, carbon is depleted. This happens when deep convection currents reach into layers where nuclear processing has already altered the composition, then drag that processed material to the surface. It's like the star turning its pockets inside out. Aldebaran is also slowly bleeding mass into space, about 1 to 1.6 times 10 to the negative 11th solar masses per year, with winds moving at 30 kilometers per second. That adds up to roughly 1 Earth mass lost every 300,000 years. Not catastrophic on human timescales, but over millions of years, it strips the star down considerably. And then there's the planet. Aldebaran B is a confirmed gas giant with a minimum mass of 5.8 Jupiter masses, orbiting at 1.46 astronomical units with a 629-day period, which raises a question that should feel personal. If Aldebaran was once a star very similar to our sun, and it expanded dramatically during its red giant phase, how did that planet survive? At 1.46 astronomical units, it's sitting uncomfortably close to where the star's outer layers would have been pushing outward. The fact that it's still there suggests planetary survival during red giant expansion is more complicated than everything nearby gets eaten. That's directly relevant to what might happen to Earth when our sun eventually does the same thing. So Aldebaran isn't the biggest red giant, or the brightest, or the most dramatic, but it might be the most important one for us personally, because it's essentially our sun's future, observable right now, only 65 light years away. But if Aldebaran is the sun's future sibling, then Arcturus is its weird older cousin, who took a very different path through life. Arcturus is an intruder, not metaphorically. This star does not belong to our neighborhood. It's a population 2 halo star, born 7.1 billion years ago in an entirely different era of the Milky Way, and it's just passing through our little corner of the galaxy at 122 kilometers per second. That's fast enough that it'll reach its closest approach to us in about 4,000 years, and then it's gone. Cosmic drive-by. But while it's here, it happens to be the brightest star in the entire northern celestial hemisphere and the 4th brightest in the whole sky, all from just 36.7 light years away, making it the second closest giant star to Earth after Pollux. Here's what makes Arcturus genuinely strange. It has almost exactly the same mass as our sun, 1.08 solar masses, basically a rounding error, and yet it shines 110 times brighter than the sun in visible light. Bump that up to include infrared radiation, and you're looking at 215 times the sun's total energy output. That gap between 110 and 215 is important, because it tells you something fundamental about red giants. They're hiding a massive chunk of their energy from your eyes. Arcturus radiates nearly half its luminosity in wavelengths humans literally cannot see. You look up at this brilliant orange star and you're only catching about half the show. Its surface temperature sits at 4,286 Kelvin, which is warmer than Aldebaran's 3,900 Kelvin, despite both being red giants of similar mass. The radius tells the real story, though. Arcturus has swollen to 25.4 solar radii, smaller than Aldebaran's bloated 45, but still enormous for a star that weighs about the same as the Sun. Two stars, nearly identical mass, wildly different sizes and temperatures. The difference comes down to where they are on the giant branch and, critically, where they came from. Because Arcturus is old, genuinely, profoundly old. At 7.1 billion years, it predates our entire solar system by over 2.5 billion years. It formed when the galaxy was younger, metal poorer, and structurally different. Its low metallicity is the fingerprint of that ancient origin, a star forged from primordial gas that had barely been enriched by earlier supernovae. And somehow, despite being a giant star, Arcturus has a detectable magnetic field. About 0.5 Gauss, which is weak, but the fact that it exists at all is surprising. Giant stars aren't supposed to maintain organized magnetic activity, their envelopes are too diffuse, their rotation too slow, but Arcturus appears to undergo a solar-type magnetic cycle with a period shorter than 14 years. Nobody fully understands why a 7 billion-year-old halo giant is doing this, so you've got a star that doesn't belong here, doesn't behave the way it should, hides half its light from you, and is older than the ground you're standing on, which is, not ideal for anyone trying to make red giants seem simple. But if Arcturus is a quiet, ancient wanderer, the next category of red giants is anything but quiet. These stars don't just change brightness, they change everything. Mira is a star that will make you distrust your own eyes, and I mean that literally, because the physical changes happening on this star are frankly modest. But the visual result is absolutely absurd. Let me explain. Mira, also known as Omicron Ceti, sits about 300 light years away in the constellation Cetus. It's a binary system. Mira A is a thermally pulsing AGB star, the kind we just talked about, and Mira B is a white dwarf companion orbiting about 70 astronomical units away. That companion is basically a preview of Mira A's own future, which is a nice little cosmic foreshadowing if you're into that sort of thing. But Mira A is the real star of the show. It's the prototype for an entire class of variable stars. Around 66,000 known Mira variables exist across the galaxy, and they're all named after this one. Every 332 days, Mira A completes a pulsation cycle where its visual brightness changes by more than 15 times. In a typical cycle, it swings from magnitude 2.0, easily visible to the naked eye, down to around magnitude 10, where you'd need a telescope to spot it at all. But here's the kicker. Across different cycles throughout its recorded history, the variation from absolute maximum to absolute minimum reaches up to 1,700 times. 1,700 times brighter at peak than at its dimmest. That's not a typo. Now here's where it gets genuinely weird. You'd expect a star that varies by 1,700 times in brightness to be doing something dramatic, exploding, collapsing, going through some kind of catastrophic event. Turns out, no. The temperature only swings between about 3,000 and 4,000 Kelvin. That's less than a 10% change. The radius varies from roughly 332 solar radii to 402 solar radii, which is significant, but still only about a 20% shift. Those are not world-ending numbers, so how do you get a 1,700 times brightness variation from a less than 10% temperature change and a 20% radius change? The answer is the Stefan-Boltzmann law and the Planck function working together in the most nonlinear way possible. Luminosity scales with the fourth power of temperature and the square of the radius, so small changes get amplified enormously. And because Mira is so cool, most of its radiation comes out in the infrared. In the visual band, you're watching the extreme tail end of its emission curve, where even tiny temperature shifts cause the visible light output to skyrocket or plummet. The infrared variability is only about 2 magnitudes. The visual variability is 15 or more. Same star, same physical changes, completely different story depending on which wavelength you're watching. It's like holding a dimmer switch that barely moves, but the light in one room goes from candle to spotlight while the light in the next room hardly flickers. Mira also holds a special place in history. It was the first non-supernova variable star ever discovered, first observed by David Fabricius back in 1596, and later given the name Mira in 1642. For over 4 centuries, astronomers have been watching this thing pulse and fade and return. And within the next few million years, it'll shed its outer layers entirely, form a planetary nebula, and collapse down into a white dwarf, just like its companion already did. But if you think Mira's brightness swings are dramatic, wait until you hear about a red supergiant that decided to just go dark one night and terrify every astronomer on the planet, Betelgeuse. This is the one you've been waiting for. Betelgeuse, the red supergiant sitting in the shoulder of Orion, roughly 548 light-years away and less than 10 million years old. For context, our sun is 4.6 billion years old and still middle age. Betelgeuse burned through its entire life cycle in a fraction of that time. It lived fast, it got enormous, and it's going to die in the most spectacular way a star possibly can. But let's talk about how enormous we're dealing with here. Betelgeuse's radius sits somewhere between 700 and 900 times the radius of the sun. If you dropped Betelgeuse into our solar system, the surface of the star would extend roughly 2/3 of the way to Jupiter's orbit. Mercury, Venus, Earth, Mars, the asteroid belt, all just inside a star. You wouldn't even need to worry about global warming because there wouldn't be a globe. The surface temperature is only about 3,450 Kelvin, significantly cooler than the sun. But what it lacks in heat, it makes up for in sheer output. Betelgeuse pumps out somewhere between 100,000 and 140,000 times the sun's luminosity. It is, by every possible metric, not a subtle object, and it doesn't sit still. Betelgeuse pulsates on multiple overlapping cycles, a main period of about 400 days, a shorter 185-day cycle, and a longer secondary period stretching to roughly 2,100 days. These pulsations cause its apparent magnitude to swing anywhere from 0.0 to plus 1.6. Some nights it's one of the 10 brightest stars in the sky. Other nights it's noticeably dimmer. The star literally can't make up its mind. Here's where it gets really interesting. In late 2019, Betelgeuse started dimming. Not the usual pulsation dip, it kept going. By February 2020, it had dropped to magnitude 1.614, the faintest ever recorded. Astronomers collectively lost it. Headlines everywhere asked if Betelgeuse was about to explode. Social media was split between genuine scientific concern and people who just wanted to see a supernova before their student loans came due. Turns out, no. The Great Dimming wasn't a death rattle. A chunk of Betelgeuse's surface cooled down, ejected material into space, and that material condensed into dust that blocked the light from reaching us. Which is, not ideal when you're trying to figure out if a star is dying or just having a bad day. But that event was genuinely important. It challenged assumptions about how stable these late-stage massive stars actually are. The mass loss mechanisms turned out to be far more episodic and chaotic than models predicted. Betelgeuse doesn't shed material evenly. It blasts stuff out in clumps. Current estimates suggest it loses roughly 1 solar mass every million years. That's the entire mass of our sun, just gone, every million years. Which sounds slow until you remember most stars don't lose that kind of mass at all. Now, for the question everyone actually wants answered, when does it blow up? The honest answer is within the next 100,000 years. Some models suggest it could happen within decades. Nobody knows for certain, and anyone who tells you they do is lying to you. What we do know is what it'll look like. When Betelgeuse finally goes supernova, it will briefly shine about as bright as a half moon. For over 3 months, visible during the day, a single point of light in Orion's shoulder, bright enough to cast faint shadows at night, and at 548 light-years away, it poses absolutely zero threat to Earth. No radiation damage, no gravitational effects, nothing. Just the most spectacular light show any human has ever witnessed. Somewhere between tomorrow and 100,000 years from now, Betelgeuse is going to put on a performance that every civilization on Earth for the rest of recorded history will remember. And there's nothing anyone can do about it except wait and watch. If you enjoyed this video and want to see more, click the video on the screen now.